Okay, let's start. So we stopped at small signal analysis for differential pair. We have done differential pair. We roughly know how it works in DC. Now we are going to use small signal analysis in differential amplifier. So our aim, I think previously when we do single stage amplifier, we are looking for V out over V in. But now, since it's a differential amplifier, we are looking for V out 1 minus V out 2 divided by V in 1 minus V in 2. So you can see the difference over here. So the first method is what we call superposition. Okay, so this is the most correct method. The second method is the very easy one, when we assume everything is ideal. Okay, so the first method, superposition. I think you guys have learned in circuit theory or something what is superposition. Means like you turn off one part, you find the other one first, and then you turn on another part, you find back the first part. So similarly, first we will turn off input number 2. So to recall, this is your differential amplifier. We will have two transistors, two common source basically. So you have V in 1, V out 1, V in 2, V out 2, and then they both are synced to the same current, meaning that ID1 plus ID2 needs to be equals to ISS. So no matter what, this ISS will tune itself to be the same as these two. So first, we will turn off V in 2. And then we will find what is V out 1 minus V in 2 due to V in 1. Because V out 2 now turned off already. V in 2 now turned off already. So we will first figure out what is V out 1 minus V out 2. So you can see we want to find out V out 1 minus V out 2 when there is only V in 1. Okay, so let's do the first step. We want to find V out 1 due to V in 1 first. Okay, because we cannot find V out 1 minus V out 2 directly. So we can find V out 1 due to V in 1 first. Basically, we are looking for V out over V in. V out over V in. Okay, so in this case, your gate of M2, we say we turn off, so it is grounded. Okay, so can we remodel this a little bit? We say this is grounded, so we can model this thing into this circuit. Okay, as in, we will have your VDD, you have your ID1, you have your V in 1, you have your V out 1, and then down there, here is the case. So you can imagine down here, you will be probably seeing something at ISS, as well as something at your M2. M2 turned off only, but it still have some it will still contribute to some resistance. Okay, so when we say we want to model this whole thing, okay, so this part plus this M2, we need to model them in terms of a resistor. So we call it RS. So this and this circuit, they are now exactly the same thing. Okay, so once you have modeled, you might be thinking, does it look like something that we have learned earlier? It is a common source amplifier with source degeneration. We learned that previously. Okay, so generally, common source with source degeneration, the formula that according to what we have derived earlier is negative GM over 1 plus GM RS times RD. So this is the gain that we have. So we do know that RD is equals to RD1. But do we know what is RS? The GM is equals to your GM1. But what is your RS in this case? So to find out what is the RS in this case, okay, so you can see RS over here is supposed to be equals to A in parallel with B, because you say B, it will also go to ground in the end when it's small signal because VDD is grounded. So A in parallel with B supposed to be equals to your RSS. So ISS is ideal current source. Last class we mentioned that if it is ideal current source, it is infinity resistance. And then for B we are seeing from M2 source to drain. We also mentioned this a lot of time. When we are seeing from source to drain, the impedance is 1 over GM. Okay, the R is 1 over GM. So this is 1 over GM2. Basically, your RS now is infinity parallel with 1 over GM2. So something very big parallel with something very small. We only care about the small part. Okay, so we can say that V out 1 over V in, finally, supposed to be equals to GM over 1, negative GM over 1 plus GM, RS times RD1. And what is your RS? Since we can ignore the infinity, now our RS is 1 over GM2. So this is your final answer for V out 1 divided by V in 1. So this is only one part of it. Remember, for superposition, first step is to find out V out 1 minus V out 2. So we found V out 1 only. Then we need to go to V out 2. So now we want to find V out 2 due to V in 1, meaning that I still turn off my V in 2, but now I want to find V out 2 due to V in 1. So meaning that is I'm finding V out 2 versus V in 1. V out 2 versus V in 1 in this case. So what exactly is V out 2 versus V in 1? We can say it is V out 2 over Vp times Vp over V in 1. Then you can cancel out the Vp. Then it is just V out 2 over V in 1. So in this case, let's look at one by one. What is V out 2 versus Vp? So we can see from here, V out 2 is over here. Vp is this point. Okay, so this is out, this is in. The input is actually going from source. Output is at the drain. So this is our common gate. Okay, common gate. When input as source, output at drain, it is our common gate. So we can say, okay, this is common gate that we have learned earlier. So we keep it first. And then what is Vp versus V in 1? Vp versus V in 1. So you can see Vp is at your source. V in 1 is at your gate. So this is your output. When this is output, when the source is output, it is common drain. It is common drain. So we got 1 and 2. Then we can do one by one. Okay. So we can say for common gate, our output, it is just GMRD. What is the GM? It will just be GM2 because now we are focusing on this transistor. Okay, the output versus input. So our amplifying transistor is this M2. So it's GM2 times RD. GM2 times RD. This RD, we can just use RD2. Okay, we can just use RD2 because in general, here is input already. So the RD is over here. Okay, for your common gate case. But for your common drain case, we say that it is V out. We can say that V out is at the source, V in at the gate, at V in 1. Okay, so it's over here at V in 1. Here is your input, and here is your output. So V out over V in of your common drain, it is equals to GM R out. GM R out. So generally, we know everything is GM R out. But what exactly is GM R out in this case? What is the amplifying transistor? It is GM1. It's this first transistor. So we call GM1. What is the R out? So here is your output. Here is your output. You have to look at everywhere that you might be seeing. From this VP point, where you'll be seeing, you can see from to the left, you can see to the right. You can see to the bottom. To the bottom, it is very straightforward. It is infinity. So to the bottom, to ground. So it is infinity. And I mentioned before, we are looking from source to drain. Source to drain. So it is 1 over GM1, parallel 1 over GM2, parallel infinity. So we know that we can cancel out this infinity when they are in parallel. So our final answer is GM1 over GM1 plus GM2. So we multiply both together. We will get GM1, GM2 divided by GM1 plus GM2, RD equals to V out 2 over V in 1. So we have found V out 1 due to V in 1. We have found V out 2 due to V in 1. So the process is very, very lengthy. Okay. So since we have found both V out due to V in 1, we can just substitute them now. So this was V out 1 due to V in 1. This was V out 2 due to V in 1. You minus them out, you get this equation. And then if if GM1 equals to GM2, in the end, you just get V out 1 minus V out 2 due to V in 1 is equals to negative GMRD times V in 1. So this is the equation that we actually need. Okay, V out 1 minus V out 2 due to V in 1 is equals to this one. If we assume GM1 is equals to GM2, means that they are quite balanced. Okay, are you guys confused so far? Okay, so I will give some time. You guys go through one by one. So this is the first part that we need to go through. So because when I am saying, you guys might not be able to follow, so I'll leave this page for a while. You guys read through, check whether you understand this part first. We are looking for V out 1 versus V in 1 in this case. And we grounded our M2 gate. Okay, so I'll give you minutes. You guys read through this one first. This part, okay? We go to the next one. Find V out 2 due to V in 1. So V out 2 versus V in 1. Okay, you only need to know the first case first. Okay, V out 2 due to V in 1. you see the common gate, we say it is GM2RD2. Common gate, generally, we know it is as GMRD without the negative part. But you might be asking, why do we not need to change the RD2 or anything? GM2 is fixed, but like other cases, we need to see parallel or something. But why in this case we don't need is because this, when we say GM2RD2, the RD2 is somewhere at the drain. So we only care at the drain. Whatever below it is the source already. So we don't care what happens at the input. That's why we straight away can use GM2RD2 directly. Okay, for common drain, it is a bit different. Common drain, we know that we always say the gain supposed to be nearly 1, but we know when there are so many components, it might not be 1. So we find out what is the GMR out. What is the GMR out? So the GM amplifying transistor is on the M1, so we put GM1. And then what is the R out? Remember that now the output is at the source, so you need to see from the source what are the output. That's why you have to see parallel, the 3 parts of it. That only you combine. Okay, so next one. If it is V out 1, so we have done the first step of our superposition. We have found we have turned off V in 2, and then we have found V out 1 minus V out 2 due to V in 1. And then now we need to turn off V in 1 and find V out 1 minus V out 2 due to V in 2. So it might look similar because it probably just the opposite way of what we have found just now. So maybe we can just find, let's say just now the answer was negative GMRD V out, V in. Then maybe now the answer will be positive GMRD V in. It's just the opposite way, so that's okay. And then it says the third step is just add number 1 and number 2 together. So we go to the next step. So V out 1 minus V out 2 due to V in 2, now it will just be positive GMRD V in 2. And then we add both of them together. You find out your differential gain. It is just negative GMRD. We go all the way around, ended up, we find our answer to be negative GMRD. So this is the tips. When you do not figure out what is the answer, probably when you write GMRD, negative GMRD, like 90% of the time you'll be correct. So even you don't know how to derive, just give me the final answer, negative GMRD, then you will have some marks at least. Okay. The next one is what we call half circuit method. Okay, so method number 1 is superposition. That's the very, very accurate one. Like even though when both V in or both V out are very different, you can still use the method. But for half circuit method, if you want to use this method, there are a few criteria. The first criteria is it must be fully symmetric. Fully symmetric as in M1 needs to be equals to M2. And then your RD1 needs to be equals to RD2. So like fully symmetric, sizing everything the same. And then it needs to be fully differential input. So V in 1 and V in 2, there must be 180 degree out of phase. Okay, so if they are fully symmetrical, we can say that P now is not affected by AC. They are cancelled out. So imagine that 100 degree, so imagine that there is a positive 1 volt going in from V in 1. There's negative 1 volt going in from V in 1. And then they combine at VP. So above ISS. So they cancel each other out already. We can say now they are basically virtually grounded. So this ISS now is grounded because they are basically cancelling each other out. So we can cut the circuit into half. So we cut this circuit into half. This is a ground. So we can split something like this. So it will be, we know when we draw small signal, ideal voltage source is grounded. So this will be grounded, and then RD1, RD2. Here is your out 1, out 2, V in 1. And then it's grounded because ISS is grounded now. Grounded. So in this case, what we want to find V in 1 minus V in 2. We want to find V out 1 minus V out 2 divided by V in 1 minus V in 2. So we can first figure out what is V in 1 minus V in 2. Based on the condition that we have mentioned, if you want V in 1 minus V in 2, it means that V in 2 is negative V in 1. So it will just be V in minus V in. So you get 2 V in the end. So this is V in 1 minus V in 2, 2 V in. Next, what is this circuit? It is a common what? Common gate, common source, common drain. Which one it is that you think? it is a common source. Okay, by now you should have directly see it, and then you can answer directly already. It's a common source because the source is grounded. Or we can say that because the gate input is your gate, output is your drain. So when input output, the third part that doesn't have input and output, that is your common one. Okay, so common source. So in this case, V out 1 minus V out 1 versus V in 1 is a common source, so it's just negative GMRD. V out 2 over V in 1, but now it's not V in 1, it is negative V in 1. So generally, output over input is negative GMRD. But since this is negative V in 1, so you cancel the in. So it becomes GM2 RD only. And then we can first figure out what is V out 1 minus V out 2 versus V in. Because this is V out 1 minus V out 2 divided by V in. Okay, we just combine these two together. So imagine if you have this and this minus, okay, it will affect the layout, so it doesn't matter. So you imagine you use V out 1 minus V out 2 divided by V in, and then this negative cancel already. So whatever that divide at the denominator is just V in. So it becomes this one. So mean it is negative GM1 RD minus GM2 RD. So it becomes negative 2 GM RD. So based on this first condition, okay, our aim is to find out V out 1 minus V out 2 divided by V in 1 minus V in 2. So we know that V in 1 minus V in 2, it is 2 V in. So we are looking for V out 1 minus V out 2 divided by 2 V in. Now we already got V out 1 minus V out 2 divided by V in. We just divide this by 2, we get negative GMRD. So back to the same one as we have derived for superposition. So they are the same answer. All right. And then coming to the last part of this chapter for differential amplifier, common mode response. So common mode response happens when non-ideal current source is used. Okay, so we always say that we will use something that is very ideal at the bottom, ISS. But common mode response, it might happen when there's non-ideal current source is used. So you imagine that when your input common source changes, your V in 1, V in 2, you connect them together. And then when it change up and down, okay, the output DC level also will change. Because you're changing the input DC, the output DC also will change. Because now, this is not ISS anymore. It is something that being powered up by external sources, by bias voltage. So we can combine, we try to combine this circuit into this one. Okay, you see, V in 1, V in 2, they are having the same voltage. So we say it is input common mode voltage. They are connected. So we can use V in common mode as the voltage source. And then there are two transistors. We combine the two transistors together, become one transistor. Now, initially it was W over L sizing. Now become 2W over L. This is a transistor. We can model them as a resistor. We call RSS. And then on top, you can see these two are basically in parallel because they will be connected to ground later. So these two are in parallel. So you need to be RD divided by 2. So we combine this into this circuit. Okay, so we can say if GM1 equals to GM2, generally GM equation that we derived in first chapter, it is equals to square root 2 mu NCox W over L ID. So now the new GM, initially if there's only like, if their DC mode is not common, okay, if it is very ideal, generally it's supposed to be just GM equals to this one. But now because of this new circuit, when we separate seeing them, okay, it's supposed to be this one. But now we can combine them already. The new GM is supposed to be 2 mu NCox. Now it is 2W over L. So you change W over L into 2W over L. Now there are two current flowing down. So it becomes 2ID equals to 2GM. So we say that in ideal case, in most ideal case, we want our DC level of both biasing point, V in 1 and V in 2, they are the same. So that when whatever input coming in, whatever AC coming in at both sides, the noise level is still the same. They're at the same DC level. So the DC cancel out. So we only amplify whatever signal that we want, whatever DC that we want. Okay. So just now that one was the ideal case. Just now the one was the ideal case because we want both common to be the same. And then we might have non-ideal current source. So this is the exact thing that we are actually looking for. Okay. So just now the circuit, I moved to downward already. Move to here already. So you can say, now this circuit, what will be the gain? Ideally, what should be the gain of this circuit? So you will realize that this looks like common source with source degeneration. Again, common source with source degeneration in chapter 2, we have learned it is equals to negative GMRD over 1 plus GMRS. So GM changed to 2GM. RD becomes RD over 2. So in the end, your final answer is negative GMRD over 1 plus 2 GMRS over 1 plus 2 GMRS. So this is the ideal gain where we want to inject the same DC level and then we cancel out all the noise. Okay, so this is the final gain. Okay, so as a practice, maybe we can do, I mean, not for differential amplifier because it is a bit complicated to draw the small signal. I'll just simply give any circuit. You guys try to find out what is the VR over Vin. It's something that we learned before. Yes, we tried this again. Find out what is the shall I confuse you guys with buy in? Let me see. I think we can do V in. I think we didn't discuss the last question last time, so we can do. Okay. We just do V in. So you have to consider all the non-idealities. Try to draw a small signal model and find the answer. I'll give you 15 minutes because this might take some time. Okay, you can refer to this small signal, check whether it's correct or not first. Like that. I thought this is RT. Okay, I'll continue. So we can first derive. So this small signal, it says that my RD, it will flow. So let's assume it will have a current flowing from bottom to top. So once it flows to the top, there's only one way to go. So it will go to these three paths in parallel. So ID, it will go to R0, GMB, VBS, and GM, BGS. These three combined. And then in the end, once they go out as one line to the bottom. So we can find this current is equal to this three add up. This current is also equal to this current. So first, we can do what is the first current. So we can say that this current flowing at RD, it is equal to, it flows from bottom to top. So it will be 0 minus V out divided by RD. So we can say 0 minus V out divided by RD first. It is equals to what? It is equals to these three add up. So GM, VGS, GMB, VBS, as well as this. So it will be V out minus VS. We call this our source voltage. So VS, V out minus VS divided by R naught. At the same time, we can also say the same current. So we just call negative VRRD. It is also flowing to the bottom. This bottom, the current flowing at RS, it will be VS minus V in divided by RS. VS minus V in divided by RS. So here's the equation that we came up so far. So we do not know what is VS. So there are a lot of unknowns still. We know we need to remove VGS, we need to remove VBS, we need to remove VS. Maybe we can start from removing VS. So what exactly is VS? So you can rearrange this equation. Okay, you can say it is VS now Okay, so maybe I'll do it here. We can say negative V out times RS divided by RD, and then you move here already. So plus V in will be equals to your Vs. Okay, so these two are the same thing. I just change a little bit to find Vs. Then now looks like I can substitute everything inside. Okay, let's first figure out what is your Vg, because we know Vgs is Vg minus Vs. We already got Vs, that's okay. And whatever at Vs here, looks like we don't need to eliminate because it is just a resistor. And then V out, V in. So what exactly is your G? Gate is grounded because it's a DC bias. So your G is equal to 0. GMB VB is always equal to 0. So looks like we can continue already. So we write negative V out. So the whatever left is just the maths. Okay, negative V out over RD is equals to GM 0 minus Vs. So it is equals to minus the whole term, minus negative V out RS over RD plus V in plus with GNB VBS. So again, it is negative V out RS over RD plus V in. What else? Plus with V out minus this whole term, negative V out RS over RD plus V in, divided by R naught. Divided by R naught. So from this equation, we rearrange to find out what is the V out over V in. So what's left is just the maths. So maybe we put V out one side. V out one side. So it is 1 over RD. So what's in V out over here? Here got V out, so it will multiply with GM. So we can say that it will be plus. So move here, it will be minus V out. So that's okay. We just move here. So it will be plus with GM RS over RD. This is V in, so it doesn't matter. We keep it first. And then here also got V out. So plus with, so again it is plus. So move here, it becomes negative. So here I remain plus. So it becomes GMB RS over RD. And then V out, it is somewhere there also. So this is actually V out minus V out. Okay, so here is V out over R naught. We just move here, we do V out over R naught first. So it will be, this is plus, so move here, it becomes negative. So we just plus 1 over R naught. And then again, that will be plus. So we move back here, so it will become plus RS R naught over RD. This is for V outside. Okay, let me double check whether it is correct or not. There are 1 over RD, GM RS RD, GMB RS RD, 1 over R naught RS over R naught. Yes, correct. Okay, so it's equals to your V in at the right hand side. So here we got GM V in. So we write it is GM. Here we got GMB. Here we got 1 over R naught. So that's it. Then V out over V in. So V out over V in, it is very straightforward now. So this over that. Okay, so we move this V in down. This we need to move to the bottom. So your gain will be equals to the negative also we move here, yeah. So negative GMB 1 over R naught divided by 1 over RD GMRS over RD, GMB RS over RD. Okay, we do not generally like there are so many denominator. So maybe you can multiply everything by RD first. You can multiply everything by RD. So it will be negative GMB 1 over R naught times RD. So the bottom RD all we can remove. So it becomes 1 plus GMRS GMB RS plus 1 over R naught. Okay, because we multiply RD and then RS R naught. Okay, so that should be a better answer to show. Okay, a lot of ways you can use also correct. I do not like R naught. You can do some more. You can times multiply with R naught some more. So if you multiply with R naught some more, then it will be not so nice. 10, still okay. So you can, it will be GM plus GMV times RD plus 1. Okay, we move the RD to the outside, okay, just plus 1. And then everything multiplied by RD. Divide by R naught plus, so I put R naught okay, so it can be both, but it might look slightly complicated. Okay, but it is okay to stop at this part as well. Okay, so to not make it so complicated, you can stop at this part. Okay, this can be answered. So yeah, let's remove this one. Too many squares. Okay, we remove this part. Okay, so all good. Right, so just in case, I'll take a photo and upload to Teams because this will be recorded. Okay. Now we can continue to chapter 4. So chapter 4 is current mirror. I think we have learned current mirror in BJT. BJT also got current mirror. If you guys can exactly mirror. Okay, what exactly is current mirror? So we see that current sources are everywhere. Chapter 4 already, yeah? Current sources are everywhere. So you can say that when the first case, this case, it looks like it is input output. So it looks like it is a common source with current load. Common source with current load at the top. And then the second one is a common drain. The third one is a common gate. So it looks like everywhere there is a current source. Current source as in, you see, this is generated by VB. Transistor is actually voltage to current converter. Okay, so you pump in voltage, it gives you current. So it gives VB, it gives you current. So basically we need some current here. We need some current here. We need some current here. So current is everywhere in amplifiers. But how do we actually generate what is the VB? How do we generate the VB? We want to generate a very ideal current, but how do we do that? There are a few ways. The first one, maybe let's say we just give a voltage source of, so we just give an ideal voltage source of VB. Then you know that once we have VB, we can have the current. The current is equals to the saturation region equation, half mu and C of W over L VGS minus VTH square. So if we at least have this current, but you can see that mu n VTH, they are very with temperature because these are the mobilities inside the electrons. So the electrons mobility might vary with temperature. So this is not very good. We think that this is not so good. Second case, we can try. We know that we need to pump a voltage. So we build a voltage divider, R1 and R2 voltage divider. So once we pump into the gate, then we will have the voltage output of R2 output to be this gate voltage. So the equation becomes IT equals to mu and C of W over L. Initially it was VGS, so it was the gate source voltage. But this gate voltage now is the voltage divider minus VTH. Okay, but you realize that now in this case, looks like I will still have my mu n VTH. At the same time, I need to care about my VDD. So it's very supply dependent. My VDD needs to give my drain. My VDD also needs to give my R1 and R2. So what we can do is we can copy current. Okay, we can just copy current from a stable current source. Okay, so the general concept of current mirror is we are mirroring current from some sources. But a very good mirror source topology is what we call band gap reference. But band gap reference is very hard to explain. Okay, it will be out of this scope. So we will. So for band gap, usually it's a set of reference current, and then so because band gap is too hard, so we will, instead of just use the band gap reference as the very ideal current source, we will assume that we already have band gap reference, and then we build current mirror to copy the current to everywhere else. So now we go to the concept of current mirror. So concept of current mirror, you can see at the circuit below, there is a diode connected. So there is a diode connected, M1, and then M2, I don't know how it connects, okay? But both of their gates are connected together. And then this IREF is basically from your band gap reference, okay? This IREF is just a very ideal current source pumping in to the drain. And then we want to figure out what is the current at X. What is the current that I will be receiving at X? First of all, we say that ID1, so the current that flows to your first transistor is IREF because they are in series. So IREF flows down to your first transistor. What exactly is IREF? IREF basically means ID. So ID is equals to half mu and C of W over L, VGS minus VTH. This is the equation we derived in first chapter. So what is ID2? ID2, we do not know what is the exact sizing yet, but we know that the current that flows through ID2 is supposed to also be half mu and C of W over L2, VGS2 minus VTH2 squared. So now if we assume VTH1 and VTH2 are the same, VGS1 and VGS2 are the same. Their VGS is the same. Okay, you can see the gate is connected together. The source is grounded. So VGS is for sure the same. If they are the same type transistor, then VTH is also the same. Okay, then in this case, can we say that, oh, this is the same already, this is the same already? And then let's say my mu and Cox all the same. Okay, so we can rearrange a bit this two equation. So let's figure out, we say that we want to find out what is VGS minus VTH1. We can say it is IREF divided by W over L because they are the same. So half mu and Cox, we can cancel them out. Okay, we cancel each other out first. So IREF divided by W over L1 is equals to VGS minus VTH. ID2 divided by W over L2 is equals to VGS minus VTH2. So I say VTH, VGS all are the same. So this is the same, this is the same. So I can say IREF versus W over L1 is equals to ID2 versus W over L2. So now we will have this equation, W over L2. So I can say ID2 divided by IREF is equals to W over L2 divided by W over L1. So if I want to find what is the current flowing at ID2, I can say it is just sizing of number 2 divided by sizing of number 1 times IREF. So now you can see I have eliminated mu n, I have eliminated VTH. I left with sizing. I can use sizing to control what is the current that can flow to my ID2. So meaning that if you want a current that is somewhat, usually we copy something smaller, okay, from IREF. So maybe you want ID2 to be half of IREF. You just put the sizing of number 2 to be 2 times smaller of number 1. So we can do this copy. Like this whole thing is a current mirror. We have a reference. So if you want like I out 1, you want also like maybe 2/3 of it, 1/10 of it. So you can adjust the sizing to branch out a lot of current mirror outside. So this is also one of the way to copy current. Okay, so I'll give you 2 minutes to digest this part. Okay, guys, take your attendance. Who are the three that haven't signed? Chen Hao. Okay. Okay, let's continue. Derive the expression of M4 current. M4 current. So now we build current mirrors. So current mirror, as in, you must make sure that as long as the gate and source they are connected, basically they are almost the same. So the current will flow from one side to another, to another, to another. So we can say, we can first go through this circuit. You can see what are the currents that will be flowing. So I know that this line is series. So I will have IREF. And M3 is connected all the way down to M2 as well. So ID2 supposed to be equal to this to ID3. So they have the same current. And then M4 will have its own current. So now we can check one by one what is ID2. What is the current flowing at M2? Just now we derived already. We say that as long as their gate and source they are connected together, it's supposed to be W over L2 divided by W over L1 times IREF. So it's W over L2 versus W over L1 times this IREF is equals to my ID2. Okay, but what is my ID3? ID3 is the same as ID2, so that's okay. So what will be my ID4? Take note that this is PMOS. This is not NMOS, this is PMOS. But I say that source and gate needs to be connected. For PMOS, it flows from source to drain. So the top one is source. So source and gate is still connected, so it is a current mirror. So it will flow from source. So it will flow from M3, all the current copied to M4. So it will just be 4 over 3 sizing times ID3 equals to ID4. So what is your ID3? ID3 is equals to ID2. So you put this whole term down. So it is very easy. So current mirror is basically the easiest chapter in this class. Okay. So I can just say I'm just copying all the currents. Okay. Then next one. Derive the voltage gain of the circuit. Voltage gain of the circuit. Okay, so it looks like a common source, or maybe not, but we can figure it out. Okay, we want to figure out what is the V out over V in. V out over V in. Okay, so you can try. So this is a current mirror. This is a PMOS, so it's at the top. Your source and the gate are connected, so it's current mirror. So we can say that ID1 is equals to ID2. So ID1 as in the current flowing at the left is equals to the current flowing at M1 is equals to the current flowing at M2. And then the current is actually your GM VGS. Okay, so you see that transistor, when there's a transistor, it is possible to be a current source. So you can see we focus on M1 first. This is a transistor. When we draw small signal model, we draw it something like this, meaning that it will give us GM VGS current. So we can say the current at ID1 is equals to GM1 VGS1, which is also GM1 V in. And ID1, ID2, they are the same. So they are the same current. And we know that this is current mirror. So ID3 is equals to size of 3 divided by size of 2 times ID2. So is times GM1 VGS1. Okay, GM1 V in. Okay, GM1 V in. So we come out with ID3 is equals to, this current is equals to GM1 V in times 3 over 2 sizing. What is V out now? What is V out now? Can we say this V out is basically what is the voltage drop at R2, R out? Okay, so I have a current flow down, ID3 flow down. So V equals to IR. I times this ID3 times my R out is equals to my V out. So 3/2 sizing GM V in times R out is equals to my V out. So what is V out over V in? You just move this V in to the other side. It will just be 3/2 sizing GM1 R out. So that's your answer. Okay, so what if lambda is not equals to 0? Lambda as in channel length modulation. So when there's channel length modulation, we say that the equation is not just now our equation stop at here. But now if we need to include channel length modulation, we have to multiply with 1 plus lambda VDS. So in that case, we can say ID2 also needs to plus with 1 plus lambda VDS2. So if VDS1 equals to VGS1 equals to VGS2, okay? So you can see that VDS, VGS over here, VDS, VGS. So you can say VDS is basically VGS, right? Because they are connected already. And it is also VGS of 2. But it is not VDS of 2. Because VDS of 2, they are not connected to anywhere. The drain of number 2 is actually somewhere. So we know that this tree is the same. This is not the same. So now we can say that IREF is not equals to your I out anymore. Or I out is not equals to your IREF anymore. But we can use this equation still using the same way as just now. Just now we say we remove this half mu NC ox W, half mu NC ox, we left with W over L. Just now we say it's equals to VGS minus VTH. But now we can say that we find VGS minus VTH square times 1 plus lambda VDS. Okay, so we know VDS cannot cancel each other out. So I can still cancel out my VGS minus VTH. But VDS, they cannot cancel each other out because my VDS2 is not equal to my VGS2. So I will leave it here. So in the end, we just be the, if we consider channel length modulation, it will be 2/1 sizing. And then 1 plus lambda VGS, VDS2 divided by 1 plus lambda VDS1. So this is the final answer when we consider. All right, so you will see that there's error factor because the VDS is there. So it looks like it is very hard for me to have ideal copy current. So the solution, what is the solution if I want to remove the VDS dependent? I can force VDS2 into VDS1. So there's one method to force VDS2 into VDS1. The method is what we call cascading. Cascoding. Okay, so cascode and as in we put left, right. We have two circuit, left and right. So let's see one by one. The first case is, so M1, M2, that forms current mirror. Okay, and then Vx and Vy. So we are trying to force Vx equals to Vy now. Vx equals to Vy now. Okay, so Vy up there, there's some current. Okay, Vy up there, there's some current, meaning that I want to use my M2 to power up some current at the top. Okay, so what exactly is Vy? Vy is equals to Vb minus VGS3, right? So it is this point minus this whole point. So it's Vb minus VGS3 is your Vy. Okay, and Vy is also equals to your VDS2. So I want to force my Vx to be the same as Vy. What I can do is I change my V bias up there. So maybe I have to have something up there to change. So I change my V bias so that my Vy can be the same as Vx. So this first method is by manual control. Okay, I manual control my Vb so that VDS2 is becoming VDS1. And then I again remove the VDD dependent. And then it looks like I'm not being affected by power anymore. I can still copy the same current. The second way is this one. This is really cascading already. Okay, cascading up and down. Current mirrors. We cascade current mirrors. Okay, so you can see we have two sets of current mirror. The top one is NMOS. Bottom one is also NMOS. Okay, so for NMOS, we check whether gate and drain now it's connected. Okay, so yes, they are connected. Gate and drain, they are connected. That forms a diode. Okay, so it looks like now we have a look at what is Vn. Okay, we have a look at what is this point Vn. We can say Vn is equals to VGS 0 plus Vx. So this Vx, whatever down there, Vx plus with VGS not is equals to Vn. At the same time, it is also equals to VGS3 plus Vy. So imagine if VGS not is equals to VGS3. Okay, if the VGS not equals to VGS3, then our Vx is equals to Vy. Okay, so we can say that once we stack them together, because this current needs to flow to here. This current also needs to flow to here. They are copying each other out. So the VGS and VGS, they are balanced already because I copied already. I still copy down there. So the voltage drop at the top is the same as the voltage drop at the bottom. So now my Vx and Vy are the same. So finally, you can say that your WOL 3 divided by number 1 is equals to 2 divided by number 1. So the bottom one is the actual operating current mirror. The top one is just to help so that my bottom current mirror has the same Vx and Vy so that it doesn't affect my VDD. This is just a complementary help. The blue color one is just to help. Okay, we will do the last question, then we'll end today's class. Okay, if IREF required 0.5 volt to operate, derive what is I out. Derive what is I out. Okay, you can have a look at the solution first. I can explain one by one later, but I want you to roughly read through first so that you are not very confused later. Okay, just keep in mind that our aim is to find out what is IREF. Okay, our aim is to find out what is IREF, because we know that once we find out what is IREF, we can find out what is IOUT, because our IOUT is the same as IREF. Okay, so it also says that given Vx is equal to Vy. So first, we can figure out what is ID. Generally, what is the equation for ID? Generally, equation for ID is this one, half mu n C off W over L VGS minus VTH squared. And then we say that IOUT is equal to IREF. Okay, so now we go point by point. Okay, point by point. What exactly is your Vx? Vx, this dot, is the same as this dot. So it's your VGS1. VGS1. To find out what is VGS1, the current that flowing through this transistor, we can go back to here. So we can say VGS1. If we put this VGS as the question, we can use ID and everything else to rephrase. So we can say VGS1 is equals to square root of 2ID over mu n C off W over L1. We derive VGS from this equation. Okay, 2ID mu n C off W over L1 plus VTH1. So this is VGS1. So far until here, is that okay? We are deriving Vx first. We go part by part. Okay, we want to know what's the voltage drop total over here. So we go part by part, we find Vx. We know it is VGS. So VGS basically is the ID current flowing. So we use back this equation. It is equal to this whole thing. Then we go one line on top. What is your Vn? Vn is supposed to be your Vx all the way down, plus with this part, right? So plus with your VGS naught. So again, I am having ID flowing down. So ID is equal to this one. So I can also say that my VGS naught is equal to all this thing, okay, plus this whole thing. I'm having the same ID flowing down. So VGS naught plus with this ID. Okay, so we end up with Vn is equal to all this long term. We can rearrange a little bit to show only L over W. Okay, we move this term up because IREF to IREF is the same. Mu n C off is the same. We move this W over L up. Okay, and then VTH1, VTH0, we need to remain. So now we can check. We know VDD is equals to 0.5 volt drop plus with Vn. We already find out what is Vn just now. From this long equation, we figure out what is Vn. So Vn, VDD will be equals to, VDD equals to 0.5 plus Vn. So we can say VDD minus the whole Vn is equals to 0.5. So what is your IREF? You can see now, if I want to derive IREF in terms of VDD and everything else, so I just, basically this equation, I just derive, put IREF out, and then it becomes this equation. Okay, I know it is a bit complicated, but I mean, this step is a bit complicated to do the maths, but I basically use this equation to find out what is IREF. So IREF is equals to, so you can see mu n C ox over 2, derived from here, and then VDD minus all this VTH, and then because here got square root, so here I square it, divide by L over W. Okay, so this is the whole term to find out what is the IREF. All right, so any question? If no, next class we can go to current mirror and then 2 more chapters. Yeah, so that's all for today, and see you guys next week.